Kind of the point of this question is to practice the idea that the r value we put into our equation has to include the distance from the center of the planet to whatever object we're measuring. So the little graphic I'm trying to show here, if the astronaut is some height, usually things are described as their height above Earth or their altitude. If we know the height of something, that's not good enough for Newton's gravity. We need to also include the radius of the Earth to give us the overall r value that will go into Newton's equation. As an example, let's say we've got an astronaut 1,000,000 meters above Earth. That is not the r value that we can put into Newton's equation. That's the height value. The r is the radius of Earth plus the height value. Excuse me. Radius of Earth is a number, you don't have to memorize numbers. It's roughly that big, 6.37 times 10 to the 6. So when we want to find our r value, we need to take the radius of Earth, the 6.37 times 10 to the 6 number, and add whatever height we were given. In this case, the height was a nice clean 1,000,000 meters. To make that math doable, you could just punch it in a calculator, but I can do that without a calculator if I think a little bit first. The first number, 6.37 times 10 to the 6. If I convert that second number, the million, if I put in scientific notation, it's a nice one. It works out to be 1 times 10 to the 6. Count over, remove the decimal, 1, 2, 3, 4, 5, 6 places. So in scientific notation, that second number, the 1,000,000, is 1 times 10 to the 6. That you can do in your head. If you had 6.37 times 10 to the 6, and you add 1 times 10 to the 6, it's just like adding 1, so we'll get 737 times 10 to the 6. If it had been 10 to the 7 or another weird exponent, if the exponents didn't match as nice, then I would probably use a calculator or think it through a little bit harder. But for this one, the 1,000,000 and the 6.37 million, they add to 7.37 million. Now it just turns into what I would call a plug and chug. We know the equation. It's just a matter of grinding it out and getting the force. Newton's gravity is Fg equals Gmm over r squared. G is a constant. I didn't type it in the example. You don't have to memorize it and look it up. It's always that 6.67 times 10 to the negative 11 number. The mass of the Earth, another constant. You don't have to have it memorized. In kilograms, it's that 597 number. And for this example, I made up that the astronaut had a mass of 80. That is on the numerator. The denominator is that r that we just figured out, the 737 number. And we have to square it. At this point, it becomes a calculator problem. Practice your calculator. If you're in class, I can maybe help you. If you're not in class, see if you can Google it or reach out to someone that knows how to work the scientific notation button on your calculator. But now it's literally just a plug and chug. You could use a Google calculator. In the previous video, I showed how it works. But once you figure out your calculator, this one should work out within rounding. It's not a ridiculous number. It ends up being roughly 587 newtons. So 2 key things. You need to learn how to use your calculator with scientific notation, and more of a conceptual thing, you need to consider the distance from the center of Earth all the way up to the astronaut. So in a case like this, you had to add the radius of Earth to the given height.